everybody. So we're going to talk about a few chapters kind of smushed into one. We're going to talk about chapters 7, 8, and parts of 8 and 9. The reason for this whole thing, this whole arc in our story in the chemistry book, is to learn how molecules will react with each other. All right, and so the basis of that is the shape of the molecule. Now, a shape of a molecule depends on what its electrons are doing, which orbitals are occupied, and for the atoms, and how those orbitals average together when you make bonds. We have all different kinds of shapes, and so it's important to learn to focus on the most important ones. The shapes of molecules are based on how the electrons are arranged in three-dimensional space. So we call that valence shell electron pair repulsion theory. So VSEPR, we call it VESPR for short. Okay, so first let's dive into a little bit of chapter 7. Okay, so in chapter 7 we learn about a few trends. I'm not going to go into great depth on each one, but it's worth reading about. The periodic table has tons of hidden kind of patterns in it, trends, one of which is size. So here I've taken the main group elements, so that's groups 1 and 2, and then 13 through 18 on your periodic table, and I've collected them all together so we can see the clear pattern here. These are just elements, right? And so I want you to answer these questions and be able to summarize the trend, right? So essentially, you can ask yourself, which side is the smallest on this periodic table of atomic radius, which is the same thing as size, and which thing is biggest? Of course, this isn't the whole periodic table. There's another row down here on the bottom that begins with francium, and so you would be able to anticipate, just kind of going down this group, that francium is going to be bigger than cesium. So these numbers represent atomic size in picometers. And so, for example, the smallest one of any of them, 37 or 31, the smallest thing is helium. And that makes sense when you think about the atomic orbitals, right? Because helium is just 1s2. So it only has 2 electrons total, and that means it's going to be pretty small. Of course, hydrogen only has 1 electron total, and it's a little bit bigger. And the reason for that is a phenomenon we call effective nuclear charge. So we'll go into that in a second. But you should be able to use this image to answer the questions here on the left. All right? And we want to remember that as we add more orbitals, you're adding another layer outside of the prior layer. And so, of course, as you go down, it's obviously getting bigger. The pattern across is less intuitive. So let's you can see what it does here in the picture, but let's think about what it means. So we have a couple of different factors when we think about effective nuclear charge. The first thing is, if I have an electron closer to the nucleus, it is going to be more strongly attracted. All right, so we talked about how electrostatic force is distance dependent. That means if you get closer, there's a stronger attraction or a stronger repulsion if these were the same charges. But we know that the nucleus, which is shown here in gray, the nucleus has to have positive charges in it, right? Lots of them. Very, very dense. One of the densest, probably the densest thing in the universe. There's an excellent TED Ed talk that walks you through the density of the nucleus. The metaphor they use is if every person on the planet had a car, and you took all those cars and smashed them down into a 1-foot cubic box, so 1 foot by 1 foot by 1 foot, all of that would be the density of every nucleus. Okay, so it's pretty dense. So we have all this dense positive charge in the middle, which is going to pull that electron. It's going to have an attraction on that electron, and the closer the electron is, the higher that attraction would be. The other factor is if we have a multi-electron system. So let's think about that. If we're comparing the same distance, right? So same energy levels. We're going to compare these two electrons and the pull that they're feeling. Okay. we have something called shielding from the other electrons. So these electrons in the middle are going to shield the outer electron a little bit. Sort of think about it as like distracting the mother, right? You've got more kids, the farther away from the mom the kid is, the less attention they're going to get. And so the nucleus here has a lot to distract it from the outer electrons. So they're going to feel less of a pull than something where you have only one electron in the outer shell. So that's factor number 2. And then the third factor is as we get, more electrons, we're also adding more protons, right? So if this was an element, not an ion, we would have 6 protons in the center. And if the bottom one is an element as well, we would only have 1 proton in the center. Oh, that's not going to work out. There we go. So 6 protons here, 1 proton here. So even with the shielding effect that's happening here in the center, what we'll observe is 6 protons is going to attract those outer electrons much, much more strongly than the 1 proton does, right? It's like the difference if I drop a quarter on the classroom floor, nobody's going to care too much. If I dropped $1 million in the front of the room, probably a lot of people would rush up to the front to get it, right? The same kind of thing happens here, except the electrons are not actually allowed to leave their orbital, right? Because that's what quantum mechanics predicts. So we have these dense positive charges in the center, and the electrons, even on the outside edge, while they feel less pull than the inner electrons do, they still get pulled. And so the more protons you have in the center, the more this pull happens. And so we can see that trend happening going across the period, right? So for example, carbon has 6 protons and lithium has 3. So lithium's charge at the nucleus is not as big of a positive charge, and that means those electrons have a little bit more freedom to roam around. So when we say things are strongly attracted, that means they're going to shrink down toward the nucleus. So as we go from the left to the right side on the periodic table, we see, due to increasing effective nuclear charge, we see that the size of the atoms gets smaller. Ions follow a little bit of a different pattern because on the right side of the periodic table, so here we have groups 16 and 17 just as examples, on the right side of the periodic table, the nonmetals have a tendency to take electrons, and the left side has the tendency to give them up. All right, so if we imagine lithium with its 3 protons, 3 electrons, it's got a size of 1.28 picometers. It's going to want to give up 1 electron to become like the noble gas before it, so that'll be helium. When it does that, when you lose an outer electron, a valence electron, it's going to get smaller. So it goes from 1.28 to 0.90. And that trend continues to happen regardless of how many electrons you give up. And you'll notice that if you make a ratio out of these, the more electrons you give up, the smaller the atom or the ion will be, right? So if we think about aluminum, which can give up 3, it's going to start out a certain size. It gives up 1, and then another one, and then another one. And the remaining electrons are going to be drawn to that very, very positive center even more than they were when it was an element. So it's going to shrink down. The nonmetals, again, they tend to take electrons. So here we have oxygen. It tends to take 2 because then it will become isoelectric. Remember that phrase? It'll become isoelectric with neon. All right, and so it starts out as an element with a distance of 0.66 from the center to the edge. That's a radius. And then it absorbs first 1 electron. This is a step-by-step process. And then 1 more electron. All right, and so this is related to a concept called electron affinity that I'm not going to cover a lot explicitly, but basically it just means that the right-hand side of the periodic table likes to take electrons, fluorine being the most likely to take electrons. And the left-hand side does not like to take electrons. They have a low affinity for electrons. Okay, so cations shrink because they give up electrons. Anions get bigger because they're gaining electrons, right? But the trend within each group is still the same. So we notice that at the top, the cation of oxygen is still way smaller than the bottom, which is tellurium. Okay? And we also notice they all take the same number of electrons when they react. It's because reactivity is the basis for the periodic table. Okay, so every time we take an electron from something, from an element, it costs a bit of energy. When we give that electron to another atom, we get some energy back. If the reaction is what we call spontaneous, if the reaction actually occurs, then that means the amount of energy you get back by giving the electrons to the anion is going to be greater than the amount of energy you spend. All right, and so the amount of energy that's required to spend to get this reaction started is called ionization energy. So, for example, for sodium and chlorine, we know that reaction happens because we put sodium chloride on our food all the time. It's table salt. In order for this reaction to get started, the sodium has to be willing to give up its electron. So this has a certain cost, right? And we have to do ionization energy one step at a time. So I just alluded to the idea that aluminum gives up 3 electrons, but it doesn't do it all at one time. So this will have a certain ionization energy, and then we'll take that aluminum plus 1 and we'll turn it into aluminum plus 2. So you can't just give up 3 electrons right away. That's the idea here. Now this happens so quickly we can't actually see, like Al plus 1, Al plus 2 with any kind of device we can use these days. Oops, it's plus 1, we go one step at a time. And so as it turns out, you can imagine if you ask me for $1, I'll probably give it to you, right? If you ask me for $2 total, one before, one now, I'll be a little reluctant, but I'll still do it. By the time we get to $3, now I'm starting to wonder why you didn't just ask me for 3 to begin with, right? And so the farther down we go, the more electrons we have lost, the more the energy requirement is. Now, if we tried to do another electron transfer from aluminum, so right here, aluminum 3 plus is isoelectric with neon? Yep. It's isoelectric with neon because it gave up 3 valence electrons. So that's very, very stable. If I try to take a 4th electron, the amount of energy to do that is exponentially higher than the amount of energy we spent to get the 3rd electron off. Okay, and so it's not that you can't make Al4+, it's that you have to spend so much energy to do it that it's prohibitive. So we can look at this as a graph. Okay, this is the first ionization energy, is what we call this. The first ionization energy is the trend across the periodic table, and so what we see here is hydrogen and helium are period 1. Lithium through neon is period 2. Sodium through argon is period 3. These are the transition metals, of course, so that's period 4. It gets longer because we have more elements to fit in. But in general, you can see that for each period, the trend is as you go from the left towards the right, just using period 1 as an example, ionization energy increases. So what this means is that it's harder to remove an electron from the noble gases than it is to remove from the alkali metals, right? So group 1 versus group 18. And that trend is generally true all the way across the periodic table, even past period 4. So we're talking about losing one electron at a time. So the reason that the noble gases are less reactive, almost not reactive, is because they have a really high ionization energy. It costs a lot of energy to take their electrons. Okay? So if we're thinking about aluminum again, this is a graphical representation of the amount of energy, and this is the data, for each ionization. So you can see we go from about 577 to lose the first electron, 1,800 or so to lose the second electron, 2,700 to lose the third. And then suddenly this spikes up to like almost 12,000 kilojoules per mole. That's really, really high. So to the scale, 2,000 to 12,000 would be way up here at the top of the website, right? And so aluminum loses 3 electrons because it becomes isoelectric with a noble gas, and we just learned noble gases have really high ionization energies. Aluminum has even more protons than neon does. So even though it's isoelectric, there's a bigger pull on the electrons that it has. So it's even less likely than neon is to give up its 4th electron. Okay. Just a little plug for this website. I think it's kind of fun. Webelements.com, and it's got cool things like enthalpies of ionization. Electron affinity is further down. But also it has our Aufbau diagrams. Now, I don't know if this includes the exceptions, but that would be an interesting thing to discover. And it also has some spectrum information. So if you had a cathode ray tube with aluminum in it, and you looked through a diffraction grating, this is what you would see. So that relates back to chapter 6.